Reproductive property of independent Poisson random variables. Property, statement, then proof, and finally application of this property in one example problem are given in this video. Before enter into the statement, we are just go through the symbolic form of the statement here. If x1 and x2 are two random variables with parameters lambda1 and lambda2, then sum of these two random variables is x1 plus x2, which is also Poisson. Parameter is lambda1 plus lambda2. But the most important condition is that two Poisson random variables are independent. Now we read the statement. The sum of two independent Poisson random variable with parameter lambda1 and lambda2 is also a Poisson variable with parameter lambda1 plus lambda2. The above property can be extended to any finite number of independent Poisson random variables. We are going to prove this starting with the two Poisson random variables x1 and x2 whose parameters are lambda1 and lambda2. With this assumption, we have to prove that x1 plus x2 is also a Poisson random variable and whose parameter is lambda1 plus lambda2. So underlined point, most important point is x1 x2 both are independent. Now we are talking about the values taken by this random variables. X1 is 0 1 2 3 etc, x2 is 0 1 2 3 etc. Then if we add these two values, we get the value of capital X, that is capital X is x1 plus x2. So again, capital X also takes the same set of values 0 1 2 3 etc, but the way in which the value arrives comes here mentioned in this table. 0 is just directly adding x1 and x2 value 0, we get the capital X equal to 0. But capital X equal to 1 means there are two ways, that is x1 0 and x2 1, or another way is x1 equal to 1 and x2 equal to 0. So the second column contains how many ways we are getting the value of capital X equal to 1. Similarly, capital X equal to 2 means either it can be obtained by adding 0 to, that is respectively for x1 and x2. So our x1 equal to 1 and x2 equal to 1 is another way. The third way is x1 equal to 2 and x2 equal to 0. Similarly, for x equal to 3 is also mentioned. So understanding this table, we can write the next consecutive steps very easily. Probability of now capital X equal to n is nothing but probability of x1 plus x2 equal to n, which means uh, either this probability of x1 equal to r and probability of x2 equal to n minus r, where this r varying from 0 to n. In this 0 to n, that means n plus 1 combinations, we can achieve the value capital X equal to n as discussed in the previous table. So simply if we mug up this step, we can't uh, understand the concept. But if we go through the previous table, it's very simple to elaborately write the summation. So probability of x1 equal to r, probability of x2 equal to n minus r can be written because these two variables are independent. So this is possible. We write the corresponding probability values here, and this e power minus lambda 1 and e power minus lambda 2 are taken out. Balance entries are given here. Now we are going to multiply this n factorial, multiply and divide by n factorial. This is because the denominator contains r factorial and n minus r factorial, which are familiar term, that is NCR related terms. But the missing one is n factorial. That's why we are multiply and divide this n factorial. The dividing n factorial is keep outside. We keep it outside, and multiplication of n factorial is taken into the summation, so that in a neat form we get n factorial by r factorial into n minus r factorial as NCR. We can write it the equivalent term, and the balance lambda 1 power r, lambda 2 power n minus r. Now this is nothing but the binomial expansion of lambda 1 plus lambda to the whole power n. So finally we are getting probability of x equal to n is e power minus, taking common minus out, lambda 1 plus lambda 2 into lambda 1 plus lambda 2 whole power n by n factorial. That is nothing but the Poisson probability mass function in the format. Instead of lambda, we are having lambda 1 plus lambda 2. It means sum of two independent Poisson variates with parameters lambda 1, lambda 2 as is also a Poisson random variable with parameter lambda 1 plus lambda 2. Here x1 and x2 are um, two independent. This is only for two variable case. If we take finite number of such independent Poisson random variables, we can extend the property to the 10 random variables, that is x1 plus x2 plus etc plus xn also a Poisson random variable with the parameter lambda 1 plus lambda 2 plus lambda 3 etc plus lambda n. This is reproductive property of independent Poisson random variables. Now we are going to see one example problem. The problem is find the probability of 5 or more telephone calls arriving in a 9-minute period in a college switchboard if the telephone calls that are received at the rate of 2 every 3 minutes follow a Poisson distribution. Given data is related to the number of telephone calls arrived in 9 minutes. Actually, data contains a 3-minute period uh, with the 2. Rate of 2 means lambda is 2. The Poisson distribution actually mentioned here is only talking about 3-minute period with lambda that is mean 2, but they are asking the question about 9-minute period, and in that period we have to find the number of calls 5 or more. So we should classify that 9-minute period as 3 3 minutes. First 3 minutes, second 3 minutes, and third 3 minutes. Totally 9 minutes. And each 3-minute category is a Poisson random variable. They are denoted as x1, x2, x3 respectively. All have common mean lambda equal to 2. The question is whether they are independent or not. We know first 3 minutes incoming arrival calls do not disturb the second one, and similarly, each of the random variable category x1, x2, x3 are mutually independent. They are independent, so we can apply the reproductive property here. Now we are taking the summation of all the three variables, which is capital X, x1 plus x2 plus x3. By the property, we have the parameter which is equal to 2 plus 2 plus 2, that is 6. So now we can write directly the probability of 5 or more calls in the 9-minute period, that is equal to a probability of x greater than or equal to 5. X greater than or equal to 5 is a very lengthy calculation area, therefore we are taking the complementary portion, that is 1 minus of p of x less than 5. That can be written as 1 minus of probability of uh, 0, 1, 2, 3, and 4. All the cases are taken and added, then subtract this quantity from 1. So respective calculation is here given. We can calculate each of the case, that is p of x equal to 0, 1, 2, 3, 4, using the probability mass function formula, that is e power minus lambda lambda power r by r factorial. Here r is respectively 0, 1, 2, 3, and 4. Calculate every quantity and add all the quantities, finally subtract it from 1. The answer is 0.7149. Hence, reproductive property is useful here because question part contains 9-minute period, but the data part contains 3-minute period. Therefore, total time is split into three segments. Each segment is taken as a separate Poisson random variable, and the sum of the three random variables is taken as the total 9 period, and we apply the property. The most important point here is the 3 3-minute period. Every 3-minute period, number of calls are independent. They are not depending on the other.